Chemical bonding. You have learnt about electron configuration of elements and periodic table in previous lessons. It was learned that there are over 115 elements. How do they usually exist? Do they exist as a single atom or as a group of atoms? In lower classes, we saw that several elements like oxygen, nitrogen, and hydrogen exist as diatomic molecules. What is the force that is holding these constituent atoms together in molecules? And you have also learned about the different laws of chemical combination. Since the formation of chemical compounds take place as a result of combination of atoms of various elements in different ways, it raises many questions. Why do some elements and compounds react vigorously while others are inert? Why is the chemical formula for water H2O and for sodium chloride NaCl? Why not HO2 and NaCl2? Why do some atoms combine while others do not? We will try to answer such questions in this chapter. Are elements and compounds simply made up of separate atoms individually arranged? Is there any attraction between atoms? What is chemical bonding? When two atoms of same or different elements approach each other, the energy of the combination of the atoms becomes less than the sum of the energies of the two separate atoms at a large distance. We say that the two atoms have combined or a bond is formed between the two. The bond is called a chemical bond. Let us take the example of common salt, NaCl. When you shake salt from a shaker, the sodium and chlorine atoms are being held together. The electrons of each atom experience the attractive force of the nucleus of the other atom. But the electrons which are negatively charged and repel each other, and the positively charged nuclei also repel each other. The strength of attraction or repulsion will decide bond formation. If attraction is more than the repulsion, then atoms combine. If repulsion is more than attraction, then the atoms do not combine. The nucleus and the electrons in the inner shell remain unaffected when atoms come close together. But the electrons in the outermost shell, that is, valence shell, of atoms get affected. Electrons in valence shell, that is, valence electrons, are responsible for the formation of bond between atoms. In previous lessons, you have studied about reactivity of elements in periodic table. Some elements are more reactive and some are less reactive. What could be the reason for the change in reactivity of elements? Let us see. Period classification and arrangement of elements in the periodic table according to the electron configuration gave a new thought about chemical bonds. Noble gases which belong to zero group, that is 18th group or 7a, are typical gases with almost negligible chemical activity when compared to other elements. They undergo few or no chemical changes. They are more stable and do not form molecules by allowing their atoms to combine among themselves or with the atoms of other elements. Consult the periodic table given in the previous chapter and fill the following table. Element Z, electronic configuration K, L, M, N, valence electron. Helium, denoted by He, 2, 2, 2. Neon, denoted by Ne, 10, 2, 8, 8. Argon, denoted by Ar, 18, 2, 8, 8, 8. Krypton, denoted by Kr, 36, 2, 8, 18, 8, 8. Look at the second columns and third columns. It is clear that all the noble gases have 8 electrons in the outermost shell, except helium, denoted by He. Lewis symbol or Lewis dot structures. The arrangement of electrons in differential of atoms, that is electronic configuration of 18 group elements, is shown in the table 1. The valence electrons in the atom of an element are depicted in a short form by Lewis symbol or electron dot structure. We represent the nucleus and inner shell electrons of the atom by the symbol of the element and electrons in the outer shell by dots or cross marks. How Lewis dot structure of argon and sodium atoms are written. Let us start with argon. Its atom has 8 valence electrons. First, write the symbol of element argon, that is Ar. Place the valence electron around the symbol. Put 2 dots at a time on each of the 4 sides of the symbol of the element till all are used up. So, we get argon. Similarly, for sodium, the number of valence electrons in sodium is 1 and the symbol is Na. We can also use cross mark for the electron. The Lewis structure for sodium atom is therefore Na. The Lewis dot structure of the atoms of noble gases is shown below. Davy's experiment. Humpty Davy in 1778 to 1819, a professor of chemistry at the Royal Institution in London, constructed a battery of over 250 metallic plates. In 1807, using electricity from this battery, he was able to extract highly reactive metals like potassium and sodium by electrolysis of fused salt. It was seen that the metal part of the compound migrated towards the negative electrode and the non-metal part towards the positive electrode. So, it was proposed that metals are responsible for positively charged particles and non-metals are responsible for negatively charged particles. The oppositely charged particles are held together by electrostatic forces in a compound. Do you agree with this explanation? Why? While this explanation could explain bonding in NaCl, KCl, etc., it could not explain bonding in carbon compounds or diatomic molecules of elements. Activity. Write the Lewis structures of the given elements in the table. Also consult the periodic table and fill in the group number of the element. element hydrogen, helium, beryllium, boron, carbon, nitrogen, oxygen. Group number 1, 0, 2, 3, 4, 5, 6. Valence electron 1, 2, 2, 3, 4, 5, 6. Lewis dot structure H, He, Be, B, C, N, O. Look at the periodic table. We can see relation between the number of valence electrons and group numbers. We find for groups 1 to 2 and 13 to 18. We can use the periodic table to find the number of valence electrons. Group 1 has 1 outer electron. Group 2 has 2 and group 13 has 3 and so on. It was found that the elements which participate in chemical reactions get octet or NS2, NP6 configuration, similar to that of noble gas elements. It is to be noted that octet rule is still a rule, not the law, because there are considerable exceptions for this rule. An octet rule, we will learn about these in this chapter. Electronic Theory of Valence by Lewis and Cousel. A satisfactory explanation of electronic theory of valence by Lewis and Cousel in 1916. They gave this concept independently. The basis for the theory was valence in terms of electrons. Observe the practical behavior of atoms of main group elements, that is, group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 0 or 8A group elements. When they are allowed to undergo chemical changes, they try to get octet electronic configuration in the outer shell. Let us understand this with the following illustrations. Group 1A elements: lithium, sodium, potassium, rubidium, cesium, and francium. Try to lose one valential electron from the atoms to form corresponding unipositive ions, which get octet in the outer shells. Example: sodium gives rise to 2, 8, 1. Sodium ion gives rise to 2, 8. Group 2A elements, that is, magnesium to barium, try to lose 2 valence electrons from the atoms during chemical changes and form dipositive ions with the octet in the outer shells. Example: magnesium gives rise to 2, 8, 2. Magnesium ion, that is Mg2+, gives rise to 2, 8. Group 3A elements try to lose 3 valence electrons from the atoms and form corresponding tripositive ions with octets in the outer shell. Example: A1 gives rise to 2, 8, 3. A1 3+ gives rise to 2, 8. Group 6A elements try to gain 2 electrons into the valence shells of the atoms during the chemical changes and form corresponding dinegative anions, which get octet in the outer shell. Example: oxygen gives rise to 2, 6. Oxygen ion gives rise to 2, 8. Group 7A elements try to gain one electron into the valence shell of the atoms during the chemical changes and form corresponding uni-anions which get octet in the outer shells. Fluorine gives rise to 2, 7, whereas fluorine ion gives rise to 2, 8. Group HA elements, the noble gases, do not try to lose or gain electrons. Generally, helium and neon do not participate in chemical changes. Even other elements of 8A do not gain or lose electrons from the atoms when they participate in a very few chemical changes. Example, neon gives rise to 2, 8. No electron gain or loss from the neon atom. What have you observed from the above conclusion about the main groups? Why do atoms of elements try to combine and form molecules? Let us see. Noble gases of 7A possess 8 electrons in the valence shell of the atoms. Helium is an exception. Its atom has only 2 electrons, but its only shell is completely filled. Noble gases with high electrons in the valence shell in the atoms are highly stable and rarely participate in chemical changes. Therefore, it is concluded that any species, that is, atom or ion, with 8 electrons in the valence shell is stable. During chemical reaction 1A to 7A, main group elements get 8 electrons in the outermost shell of the ions. Similar to noble gas atoms, it cannot happen accidental. 8 electrons in the outermost shell definitely gives stability to the ion or atom. Based on the above observation, a statement known as the octet rule formed. Octet rule. Lewis and Kossel provided logical explanation of valence on the basis of the lack of chemical activity of noble gases, which led to the proposal of octet rule. It may be stated as the atoms of elements tend to undergo chemical changes that help to leave their atoms with 8 outer shell electrons. Lewis depicted the atoms in terms of a positively charged kernel. Kernel is the nucleus and all other electrons in the atom except the outermost shell electrons, and the outer shell that could accommodate a maximum of 8 electrons. Chemically active elements do not have an octet of electrons in the valence shell of the atom. Their reactivity arises from their tendency to achieve the octet by forming bonds either with atoms of their own type or with atoms of other elements. Ionic and covalent bonds with Lewis dot formulae. Ionic bond. Kossel proposed the ionic bond, that is, electrostatic bond, based on the following facts. Ionic bond is formed between atoms of 2 dissimilar elements due to transfer of electrons from the atom of one element to the other. They are highly reactive metals like alkali metals, group 1A, and highly reactive nonmetals like halogen, group 7A, on the left side and right side of the periodic table respectively. Noble gases, except helium, have 8 electrons in the valence shell of their atoms. They are chemically inactive and stable. To attain 8 electrons in the outermost shell, similar to noble gases, metal atoms that have 1, 2, or 3 electrons in the valence shell generally lose those electrons and form stable positive ions called cations. Example: sodium 2H1, sodium ion 2H, magnesium 2H, magnesium ion 2H, aluminium 2H3, aluminium ion 2H. To attain 8 electrons in the outermost shell, non-metal atoms that have 5, 5 or 7 valence electrons gain 3, 2 or 1 electron respectively and form negative ions known as anions. Example: P phosphorus 2H5, phosphorus ion 2Ha, sulfur 2H6, sulfur ion 2H8, chlorine 2H7, chlorine ion 2H8. Do you know the number of electrons lost from a metal atom is the valence of its element, which is equal to its group number? Example: sodium and magnesium have valence 1 and 2 respectively. The number of electrons gained by a non-metal element for its atom is its valency, which is equal to 8, its group number. Example: the valency of chlorine is 8 minus 7 equals to 1. Formation of ionic bond. The positive ions, also known as cations, and negative ions, known as anions, that are formed due to the transfer of electrons from the metal atoms to the non-metal atoms, experience the electrostatic forces and get attracted to form chemical bond. As this bond is between charged particles known as ions, it is called ionic bond. Sometimes, based on the forces being electrostatic, the bond is also called the electrostatic bond. As the valence constant has been explained in terms of electrons, it is also called the electrovalent bond. Thus, we can define ionic bond as follows: the electrostatic attractive force that keeps cation and anion, which are formed from metal atoms and non-metal atoms due to transfer of electrons, together to form a new electrically neutral compounds, is called ionic bond. Explain the formation of ionic compounds: NaCl, MgCl2, Na2O and Al-F3 through Lewis electron dot symbol. Formulae: formation of sodium chloride, NaCl. Sodium chloride is formed from the elements sodium and chloride. It can be explained as follows: Na plus half Cl2, Na solid plus half Cl2 in gaseous state gives rise to NaCl in solid state. Cation formation: when sodium, denoted by Na, and gets electron configuration, it forms a cation Na+ and gets electron configuration that of neon, denoted by Ne atom. Na in gaseous state gives rise to Na+ ion in gaseous state. Electron configuration: 2, 8, 1, 2, 8, or neon 3s1 or Ne 3s1 Ne. anion formation. Chlorine has shortage of one electron to get octet in its valence shell. So, it gets the electron from sodium atom to form anion and gets electron configuration as that of argon, denoted by Ar. Cl in gaseous state plus 1 electron gives rise to chlorine ion in gaseous state. Electronic configuration 2, 8, 7 or Ne 3s2 3p5 Ne 3s2 3p6 or Ar. Formation of the compound NaCl from its ions. Transfer of electron between sodium and chlorine atoms result in the formation of sodium and chlorine ions. These oppositely charged ions get attracted towards each other due to electrostatic forces and form the compound sodium chloride, denoted by NaCl. Na plus in gaseous state plus Cl minus in gaseous state gives rise to Na plus Cl minus in solid state or NaCl. Formation of magnesium chloride MgCl2. Magnesium chloride is formed from the elements magnesium and chloride. The bond formation MgCl2 in brief using chemical equation is as follows. Mg in solid state plus Cl2 in gaseous state gives rise to MgCl2 in solid state. Cation formation Mg in gaseous state gives rise to Mg2 plus in gaseous states plus 2 electrons. Electronic configuration 2, 8, 2, 2, 8 or Ne 3s2 Ne. Anion formation 2Cl in gaseous state plus 2 electrons gives rise to 2Cl in gaseous state. Electronic configuration 2, 8, 7, 2, 8, 8 or Ne 3s2 3p5 Ne 3s2 3p6 or Ar. The compound MgCl2 formation from its ions. Mg2 plus gets Ne configuration and each Cl gets Ar configuration. Mg2 plus in gaseous state plus 2Cl minus in gaseous state gives rise to MgCl2 in solid state. One magnesium atom transfers 2 electrons, one each to 2 Cl atoms, and so form Mg2 plus and 2 Cl minus attract to form MgCl2, that is magnesium chloride. Formation of disodium monoxide, denoted by Na2O. Disodium monoxide formation can be explained as follows. Cation formation, that is Na plus formation 2 Na in gaseous state gives rise to 2 Na plus in gaseous state plus 2 electrons. Electronic configuration 2, 8, 1, 2, 8 or Ne 3s1 Ne. Anion formation O2 minus, the oxide formation O in gaseous state plus 2 electrons gives rise to O2 minus in gaseous state. Electronic configuration 2, 6, 2, 8 or Ne 2s2 2p4 He Na2, sp6 or Ne. The compound Na2O formation from its ions is as shown. 2 Na plus in gaseous state plus O2 minus in gaseous state gives rise to Na2O in solid state. Two sodium atoms transfer one electron each to one oxygen atom to form two sodium ions and two oxygen ions. Each sodium ion gets any configuration and oxygen ion gets any configuration. These ions, 2 Na plus and O2 minus, attract to form Na2O. The arrangement of ions in ionic compounds. How do cations and anions of an ionic compound exist in its solid state? Let us explain this with sodium chloride as our example. Do you think that pairs of sodium ion and chlorine ion as units would be present in the solid crystal? If you think so, it is not correct. Remember that electrostatic forces are non-directional. Therefore, it is not possible for one sodium ion to be attracted by one chlorine ion and vice versa. Depending upon the sign and charge of a particular ion, number of oppositely charged ions get attracted by it, but in a definite number. In sodium chloride crystal, each sodium ion is surrounded by 6 chlorine ions and each chlorine ion by 6 sodium ions. Ionic compounds in the crystalline state consist of orderly arranged cations and anions held together by electrostatic forces of attractions in 3 dimensions. The crystal structure of sodium chloride is given below. NaCl is said to possess face-centered cubic lattice crystal structure. The number of ions of opposite change that surround a given ion of given charge is known as the coordination number of the given ion. For example, in sodium chloride crystal, the coordination of sodium ion is 6 and that of chlorine ion is also 6. Factors affecting the formation of cation and anion. Recall the facts and variations about metallic and non-metallic character of elements. Generally, elements of metals have tendency of losing electron to attain the octet in the valence shell. This property is called as the metallic character or electropositivity. Elements with more electropositive character from cations. Similarly, non-metals like oxygen denoted by O, fluorine denoted by X, and chlorine denoted by Cl acquired electron configuration of elements of inert gases by gaining electrons. This property is called the non-metallic character or electronegativity of the element. Elements with more electronegative character form anions. Can you explain the reasons for all these? Ionic bond is formed between atoms of elements with electronegativity difference equal to or greater than. In ionic bond formation, you have noticed the atoms either lose electrons or gain electrons to attain octet in valence shell. That is, in an ionic bond, transfer of electrons takes place between combining atoms. The tendency of losing electrons to form cations or gaining electron to form anions depends on the following factors: atomic size, ionization potential, electron affinity, electronegativity, elements with low ionization energy, low electron affinity, high atomic size, and low electronegativity form cations. The atoms of elements with high ionization potential, high electron affinity, small atomic size, and high electronegativity form anions. Covalent bonds. G. N. Lewis proposed that atoms of some elements could achieve an octet in their valence shells without transfer of electrons between them. They can attain octet configuration in their valence shells by sharing the valence electrons with one or more atoms. Formations of two fluorine atoms which form a stable molecule. Each fluorine atom contributes one electron for bonding, and the electron pair that is formed in this way is mutually shared by both the fluorine atoms. Each atom in the F2 molecule has an octet of valence electrons. The dots around fluorine atom show the valence electrons of respective atoms. The chemical bond formed between two atoms by mutual sharing of a pair of valence shell electrons so that both of them can attain octet or duplet in the valence shell is called the covalent bond. Formation of O2 molecule. The electronic configuration of O is 2,6. Oxygen atom has 6 electrons in its valence shell. It requires 2 more electrons to get octet in its valence shell. Therefore, oxygen atoms come close, and each oxygen atom contributes 2 electrons for bonding. Thus, there exist 2 covalent bonds between 2 oxygen atoms in O2 molecule, as there are 2 pairs of electrons shared between them. We can say that a double bond is formed between 2 oxygen atoms in O2 molecule. Observe the following figures. Both the oxygen atoms have octet in the valence shell. Formation of methane molecule. In the formation of methane, CH4 molecule, carbon contributes 4 electrons, 1 electron to each hydrogen atom, and 4 hydrogen atoms contribute 1 electron each. Thus, in CH4 molecule, there are 4 CH covalent bonds as shown below. Formation of water molecule, H2O. In water molecule, H2O, there are 2 OH single covalent bonds. Electron configuration of O is 2, 6 and H is 1. Oxygen atom needs 2 electrons to attain octet in its valence shell. Therefore, it shares 2 electrons with 2 hydrogen atoms to form water molecule. The total number of covalent bonds that an atom of an element forms is called its covalency. The bond lengths and bond energies of covalent bonds. Bond length or bond distance is the equilibrium distance between the nuclei of 2 atoms which form a covalent bond. It is generally given in nanometer or angstrom unit. Its length equals to 10⁻⁻10 or 0.1 nanometer. That is, 1 nanometer equals to 10⁻⁹ meter or 100 picometer. Bond energy or bond dissociation energy is the energy needed to break a covalent bond between 2 atoms of a diatomic covalent compound in its gaseous state. Drawbacks of electronic theory of valence. When a covalent bond is formed between any 2 atoms, irrespective of the nature of the atoms, the bond lengths and bond energies are expected to be the same. This is because any covalent bond between any two atoms is a result of mere sharing of two identical electrons. But practically, it was observed that bond lengths and bond energies are not same when the atoms that form the bonds are different. What do you understand from bond lengths and bond energies? Are the values not different for the bonds between different types of atoms? The theory could not explain why Cl PeCl in BeCl2 is 180 degrees, FbF in BF3 is 120 degrees, HCH in CH4 is 109 degrees 28 minutes, HNH in NH3 is 107 degrees 18 minutes, and HOH in H2O is 104 degrees 31 minutes, etc. That is, it fails to explain the shape of the molecules. Valence share electron pair repulsion theory to explain the bond angle in the molecule with three or more than three atoms, with all atoms attached to a central atom through covalent bonds, a theory called the valence shell electron pair repulsion theory, abbreviated as VSEPRT, was proposed by Sedgwick and Powell in 1940. It was further improved by Gillespie and Niol in 1957. This theory suggests the following points. VSEPRT considers electrons in the valence shell which are in covalent bonds and in lone pairs as charged clouds that repel one another and stay as far as possible. This is the reason why molecules get specific shapes. If we know the total number of electron pairs in the valence shell as covalent bonds and lone pairs in the central atom, it will help us to predict the arrangement of those pairs around the nucleus of the central atom, and from that the shape of the molecule. Lone pairs occupy more space around the central atom than bond pairs. Lone pair means unshaped electron pair or non-bonding electron pair. These attracted to only one nucleus, whereas the bond pairs is shaped by two nuclei. That the presence of lone pairs on the central atom causes slight distortion of the bond angle from the expected regular shape. If the angle between lone pair and bond pair increases at the central atom due to more repulsion, the actual bond angles between atoms must be decreased. If two bond pairs are present in two covalent bonds around the nucleus or the central atom without any lone pairs in the valence shell, they must be separated by 180 degrees to have minimum repulsion between them. Then the molecule would be linear. If three bond pairs are there in three covalent bonds around the nucleus of the central atom without any lone pairs, they get separated by 120 along three corners of a triangle. Therefore, the shape of the molecule is trigonal planar. If there are four bond pairs in the valence shell of the central atom, the four bond pairs will orient along the four corners of a tetrahedron. That is three-dimensional arrangement, and the bond angle expected is 10,928. Example, methane. In methane molecule CH4, HCH is 109 degrees 28 minutes. Because of four electron pairs bonding around carbon as shown below. If there are three bond pairs and one lone pair, that is unshaped electron pair, then the lone pair occupies more space around the nucleus of the central atom. The remaining three bond pairs come relatively closer as in NH3 molecule. Example, ammonia. In ammonia, NH3 molecule, there are 3 bond pairs in covalent bonds. 3 NH around the nucleus of the nitrogen atom and 1 lone pair. Lone pair bond pair repulsion is greater than bond pair repulsion. Therefore, NH3, which is expected to be tetrahedral with 4 electron pairs, since the valence shell and HNH equals to 109 degrees 28 minutes. It has HNH equals to 107 degrees 48 minutes due to the more repulsion by lone pair of the bond pairs. The shape of the NH3 molecule is trigonal pyramidal with N at the apex of the pyramid. If there are 2 bond pairs and 2 lone pairs of electrons around the nucleus of the central atom in its valence shell, lone pair repulsion is greater than lone pair bond pair repulsion. Therefore, the angle between bond pairs further decreases. Example, water. In water molecule H2O, there are 4 electron pairs around the nucleus of oxygen atom, but 2 of them are lone pairs and 2 bond pairs. Therefore, H2O molecule gets V-shape or bell shape or angular instead of tetrahedral shape as that of CH4 due to lone pair and lone pair bond pair repulsion. HOH is 104 degrees 31 minutes. What is the bond angle in a molecule? It is the angle subtended by 2 imaginary lines that pass from the nuclei of 2 atoms which form the covalent bonds with the central atom through the nucleus of the central atom at the central atom. Note, did you notice that in BeCl2 and BF3, the central atoms, beryllium and boron, did not possess 8 electrons around them in the valence shell. They have only 4 and 6 electrons respectively. These molecules are known as electron deficient molecules. Valence shell electron pair repulsion theory VSEPR mainly fails in explaining the strengths of the bonds. This is because the theory still depends on the Lewis concept of covalent bond formation. It could not say anything extra about the electronic nature of covalent bonds. Valence bond theory. To describe covalent bonding, a quantum mechanical model called valence bond theory has been suggested by Linus Pauling in 1954. It is explained as follows. A covalent bond between 2 atoms is formed when the 2 atoms approach each other closely and one atom overlaps its valence orbital containing unpaired electron. The valence orbital of the other atoms that contains the unpaired electron of opposite sign. The so formed paired electrons in the overlapping orbital are attached to the nuclei of both the atoms. This bonds the 2 atoms together. Example, in the formation of H2 molecule, the 1s orbital of one H atom containing an unpaired electron overlaps the 1s orbital of the other H atom containing unpaired electron of opposite spin giving H2H bond and H2 molecule. The greater the overlapping of the orbital that form the bond, the stronger will be the bond. This gives a directional character to the bond when other than s orbitals are involved. Each bonded atom maintains its own atomic orbital, but the electron pair in the overlapping orbital is shared by both the atoms involved in the overlapping. If 2 atoms form multiple bonds between them, the first bond is due to the overlap of orbitals along the internuclear axis giving a stronger sigma bond. After formation of sigma bond, the other bonds are formed due to the overlap of orbitals sidewise or laterally, giving weaker pi bonds. The sigma bond is stronger because the electron pair shape is concentrated more between the two nuclei due to end-to-end or head-on overlap and attracted to both the nuclei. The pi bond overlap gives a weaker bond due to the lateral overlap of p orbital, which is not to greater extent. Consider Cl to Cl molecule. Cl 1s2, 2s2, 2p6, 3s2, 3px2, 3py2, 3pz1. In the formation of Cl2 molecule, the 3pz orbital of one chlorine atom containing an unpaired electron overlaps the 3pz orbital of other chlorine atom that contains unpaired electron of opposite spin. Formation of N2 molecule. N has electronic configuration 1s2, 2s2, 2px1, 3py1, 3pz1. Suppose that px orbital of one n atom overlaps the px orbital of the other n atom, giving alpha px to px bond along the internuclear axis. The py and pz orbitals of one n atom overlap the py and pz orbital of other n atom laterally, respectively perpendicular to internuclear axis, giving pi py to py and pi pz to pz bonds. Therefore, N2 molecule has triple bond between two nitrogen atoms. Formation of O2 molecule. O has electronic configuration 1s2, 2s2, 2px2, 3py1, 3pz1. If the py orbital of one O atom overlaps the py orbital of other O atom along the internuclear axis, a sigma py to py bond, sigma py to py is formed. Pz orbital of one O atom overlaps the pz orbital of other O atom laterally, perpendicular to the internuclear axis, giving a pi pz to pz bond. O2 molecule has a double bond between two oxygen atoms. Valence bond theory, hybridization. Formation of BeCl2, beryllium chloride molecule. Beryllium has electronic configuration 1s2, 2s2. It has no unpaired electrons. It is expected not to form covalent bonds, but it forms two covalent bonds, one each with two chlorine atoms. To explain this, an excited state is suggested for beryllium in which an electron from 2s shifts to 2p level. Electronic configuration of 4 beryllium 1s2, 2s1, 2px1 and Cl 1s2, 2s2, 2p6, 3s2, 3px2, 3py2, 3pz1. If beryllium forms two covalent bonds with two chlorine atoms, one bond should be sigma 2s to 3p due to the overlap of 2s orbital of beryllium, the 3pz orbital of one chlorine atom. The other bond should be sigma 2p to 3p due to the overlap of 2px orbital of beryllium atom, the 3p orbital of the other chlorine atom. As the orbitals overlapping are different, the bond strengths of two beryllium to chlorine must be different, but both bonds are of same strength and Cl-BeCl is 180 degrees. The hybridization of BeCl2 can be explained in this way also. Beryllium atom in its excited state allows its 2s orbital and 2px orbital which contain unpaired electrons to intermix and redistribute to two identical orbitals. As per Hund's rule, each orbital gets one electron. The new orbitals based on the types of orbitals that have undergone hybridization are called sp orbitals. The two sp orbitals of beryllium get separated by 180 degrees. Now each chlorine atom comes with its 3pz1 orbital and overlaps it. The sp orbitals of beryllium forming two identical beryllium to chlorine bonds, sigma sp to p bonds, Cl equals to 180 degrees. Both the bonds are of same strength. Formation of BF3 molecule. 5b has electronic configuration 1s2, 2s2, 2px1. The excited electronic configuration of 5b is 1s2, 2s1, 2px1, 2py1. As it forms three identical BF bonds in BF3, it is suggested that excited boron atom undergoes hybridization. There is an intermixing of 2s, 2px, 2py orbital and the redistribution into three identical orbitals called sp2 hybrid orbitals. For three sp2 orbitals to get separated to have minimum repulsion, the angle between any two orbitals is 120 degrees at the central atom, and each sp2 orbital gets one electron. Now three fluorine atoms overlap their 2pz orbitals containing unpaired electrons F9, 1s2, 2s2, 2px2, 3py2, 3pz1. The three sp2 orbitals of p that contain unpaired electrons to form 3 sigma sp2 p bonds. Shape of water molecule. It is found that HOH 104 degrees 31 minutes. The electronic configuration of HO is 1s2, 2s2, 2px2, 2py1, 2pz1 and 1H is 1s1. Therefore, there should be 2 sigma s2p bonds. Due to the overlap of s orbitals of two hydrogen atoms, the p orbitals of oxygen atom which contain unpaired electrons, HOH should be 90 degrees, but HOH observed is 104 degrees 31 minutes. To explain this, sp3 hybridization is suggested for the valence orbitals of O atom. 1s orbital, 2s and 3p orbital, 2px, 2py, 2pz intermix and redistribute into four identical sp3 orbitals, get pairs, and two sp3 orbitals get one electron each. Now the two sp3 orbitals of O atom overlap the s orbitals of two hydrogen atoms to give sigma sp3 to s bonds. Due to the lone pair repulsions and lone pair bond repulsions, HOH decreases from 109 degrees 28 minutes. Expected for sp3 tetrahedral hybridization to 104 degrees 31 minutes. Properties of ionic and covalent compounds. Property: NaCl ionic, HCl polar covalent, C2H6 covalent. Formula mass 58.5, 36.5, 30. Physical appearance: white crystalline solid, colorless gas, colorless gas. Type of bond: ionic, polar covalent, covalent. Melting point: 801 degrees Celsius, minus 115 degrees Celsius, minus 183 degrees Celsius. Boiling point 1413 degrees Celsius. Minus 84.9 degrees Celsius. Minus 88.63 degrees Celsius. Solubility: soluble in polar solvents like water and insoluble in non-polar solvents. Soluble in polar solvents like water and to some extent in non-polar solvents. Soluble in non-polar solvents but insoluble in polar solvents like water. Chemical activity: highly reactive in polar solvents and reactions are instantaneous. Moderately reactive: slow or very slow at room temperature. From the above table, we understand that ionic compounds like NaCl are solid at room temperature. Polar compounds like HCl possess properties like melting point, boiling point, reactivity, solubility, etc. between those of ionic compounds and covalent compounds. If the covalent bond is between atoms of two different elements, the shared electron pair shift more towards the atom of more electronegative element. Thus, within the molecule, the more electronegative atom bears a partial negative charge and the less electronegative atom bears a partial positive charge. A molecule of this type, which is neutral but possesses partial charges on the atoms within the molecule, is called a polar molecule, and the bond is called a polar covalent bond, or partial ionic and partial covalent bond. Example: H plus Cl gives rise to H plus Cl minus ion. In ionic compounds, there exist stronger electrostatic forces of attraction between the oppositely charged ions of these compounds. Therefore, they are solids with high melting points and boiling points. Based on the principle, like dissolves in light, they being highly polar, soluble in polar solvent. In chemical reaction of solution of ionic compound, simply rearrangement of ions take place in the solution. The reactions are instantaneous or very fast. The forces of attraction among covalent molecules are weak. Therefore, the covalent compounds are gases or liquid at room temperature. They have low melting point and low boiling points. Based on the principle that, like dissolve in light, these covalent compounds are soluble in nonpolar solvent because of nonpolar nature of solvents molecules. In chemical reactions of covalent compounds, there exists bond breaking and bond forming to get products. Therefore, these reactions are moderate or very slow. Light dissolves in light means what type of chemical bonds are there in the solute particle? The solute could be soluble in the solvent, which has the similar type of chemical bonds in its molecules.